The line L1 has equation of this, which I will immediately rewrite in column vector notation, like so. Line L2, where s is a constant and lambda and mu are scalar parameters, given that they both lie in a common plane pi1, show that an equation for pi1 is this. To get an equation for pi1, we want the normal direction for the plane, and we can get that by crossing two direction vectors in the plane, and given that both of the lines are in the plane, we can use their direction vectors. So we're crossing 1, 0, 3 from L1, and 1, minus 2, 1 from L2, and this will give us the normal direction of the plane. Crossing these, we get 0 minus minus 6, 3 minus 1, and minus 2 minus 0. 6, 2, minus 2, but this is a direction, so we don't need those exact numbers so long as the relationship is true, so we can simplify that to 3, 1, minus 1 if we want to. Then to get an equation of the plane, we use r dot n is equal to a dot n, and because both lines are in the plane, both of the points that they use are in the plane. We could use either one, but seeing as we don't know what s is, let's take 1, 1, 1 from r1, which gives us here 1, 1, 1, and n, 3, 1, minus 1. Over here, r is the general x, y, z, and 3, 1, minus 1 again. So we get 3x plus y minus z is equal to 3 plus 1 minus 1. And that's just a 3. 3x plus y minus z equals 3 is an equation for pi1, and that does match what we need. Part B, find the value of s. We can do this because we could have taken this other point, and that dot with the normal must also give us 3. So now we can do that knowing that we've got the 3 and work out s. 3, 1, minus 1 dot to s0, just as we did here, that must equal 3. And whereas before we were trying to show it, so we couldn't use s because we didn't know what s was, now that we know it's true, we can use that fact to find s. So this must equal 3. This is part B. So 3 times 2 plus 1 times s plus minus 1 times 0 equals 3. Gives us s is equal to negative 3. Part C, the plane pi2 has equation this. Find an equation for the line of intersection of pi1 and pi2. The line of intersection of two planes is in the direction that is perpendicular to both of their normals. So if I call this n1 for pi1, then n2 from the equation here is 1, 1, minus 2, and to get the direction vector of the line of intersection, I need to cross n1 and n2. So that's 3, 1, 1, 1, 1, 2, and we are crossing these two to get the direction vector of the line. It's minus 2, minus minus 1, minus 1, minus minus 6, and 3 minus 1. Minus 1, 5, 2. So that's the direction vector of the line of intersection, but we also need a point. Now we can't guarantee that the 2 points we've got are on the line of intersection, but we've got the equation for both planes. Now there's a few different ways you can find this point, but all I'm going to do is take the equations of the planes and put them together. Because here, if I rewrite this one in the same style, that's x plus y minus 2z equals 3, and for whatever reason it just sort of jumped out at me that if I subtract these two, both the y and the 3's will disappear. Then we'll have a relationship between x and z, and we can just choose any point that satisfies that and make sure that the y agrees. So here we've got 3x plus y minus z equals 3, x plus y minus 2z equals 3, and I'm just going to subtract them. 2x plus z equals 0, so z is equal to negative 2 lots of x. So I can choose any number here, and all I need to check is that it works in both of those equations. So if I say let x equal 1, then z is forced to be minus 2 because of this relationship here, and then I just put it into these two equations and check that it works with the same y value. Here that gives 3 plus y plus 2 equals 3, so y must be a minus 2. In the second one it will give 1 plus y plus 4 equals 3, and y is still a minus 2. So this will work. The point I'm going to use is 1, minus 2, minus 2. Together with the direction vector that's still on the screen there, the equation of our line of intersection is 1 minus 2 minus 2 plus some parameter of minus 1, 5, 2. Part D. Find the acute angle between pi 1 and pi 2, giving your answer in degrees to 3 significant figures. To find the acute angle between two planes, if I attempt to draw them here, see how this goes. Kind of. To get the acute angle between these two, what we want to do actually is to take their normal directions and find the acute angle between the normal directions. And to do that, we do what we normally do. We do the dot product. n1 dot n2 is the magnitude of the one times the magnitude of the other times cosine of the angle between them. And we have the two normals somewhere. There they are, 3, 1, minus 1, and 1, 1, minus 2. So if we dot these and take the magnitude, that's 3 plus 1 plus 2 is equal to the root of 11 times the root of 6. So cos theta is equal to 6 over root 66. And in degrees, that is 42.392, so 42.4 to 1 decimal place.